there's always going to be a trig equation that relates the variables together. In this case, it'll either be a sine equation, a tangent theta equation, or a cosine theta equation. Okay. Next up, we're going to differentiate with respect to time t. So remember with the very first example that we did with related rates back when we did our notes was the ladder problem with Pythagorean theorem, where x squared plus y squared equals z squared. And then when we find the derivative, 2x, and then we attach dx dt, dy dt, dz dt. So it's kind of like implicit differentiation, but instead of x being the independent variable, it's time being the independent variable. So we multiply everything with respect to time. So we have a d over dt for every variable. Okay, and then this fourth step we haven't seen before because we haven't seen trig equations or trig related rates, is that we have to use trig ratios to substitute in the values and solve for the variable. So step number 4 will feel new because we haven't seen problems that use that particular step. But the nice thing about trig related rates is that it's always going to be a right triangle, and you're really just trying to figure out, okay, should I be using sine, should I be using cosine, or should I be using tangent? Some problems allow you to pick and choose. Sometimes you have more than one option available. Other times you're forced into one trig equation because you don't have enough information to do other trig equations. Okay. All right, let's look at example 1. Okay, a fish is being reeled in at a rate of 1 foot per second from a point 15 feet above water. At what rate is the angle between the line and the water changing when there's a total of 25 feet of line out? So the triangle is here. Okay. So if I, so this distance from the top of this fishing pole to the top of the water is going to stay constant all the way through. We know that, kind of imagine as the line is reeled in, this distance is getting shorter, this distance is getting shorter, and also theta is getting larger, right? The further he's away, the further the fish is away, the theta value is going to be smaller, but as it gets closer, it's going to get wider and wider. Okay, so we know that theta is changing, z is changing. Okay, but this 15 is staying constant. Let's switch over to another triangle so we can just kind of focus on the details of this triangle. With trig equations, we don't need all 3 sides. We just need to have enough information to from 2 sides to create our trig equation, right? It's either opposite over adjacent, opposite over hypotenuse, or adjacent over hypotenuse. Okay. All right, so a fish is reeled in at a rate of 1 foot per second. What do you think this is referring to? Good, dz dt. You know this is a rate, so it can't be that constant, but it's related to z, so it's dz dt. Okay, positive or negative? Because getting smaller, right? Z is decreasing in length. Uh, 15 feet above water, so we know that's the constant there. At what rate is the angle between the line and the water changing? What are we looking for? D theta dt, right? At what rate is the angle changing? So we're looking for d theta dt. So anytime d theta dt is involved, you know that it's going to be a trig related rates problem. That's the unknown. When there is a total of 25 feet of line out. See, now this is a moment in time. Is the line always going to be 25 feet? No, right? Just the moment in time. So we don't want to put 25 in for Z. We don't want to lose that Z variable, because if we lose that Z variable, we're basically saying that this Z is never changing, and we know that's not true, right? We know 15 is never changing, but we want to hold on to variables if we know that it's going to be a different value at a different moment of time. Okay, so we have everything that we need. We want to pick a trig equation that's going to hit these three values. So which trig equation is most appropriate for us? Sine, right? Sine of theta equals opposite over hypotenuse. Okay. Now, there are times when you have more than enough information where you can pick other trig equations and all could work. But in this case, we're kind of forced into sine because we don't have enough information about what's happening here. Okay, so we'll pick sine of theta equals 15 over Z. Okay, we want to find the derivative. We're expecting d over dt to show up. The left side, we should be able to recognize the derivative rule here, but the right side, what rule should we use for the derivative? Yeah, quotient is possible, but is there an easier way? Easier one, yeah. This one, I would say power rule, because we can avoid quotient rule by bringing that z up. Now, if there were more than one term in the denominator, like z plus 1 or something, then we're forced into quotient rule. But here, or we could still do chain rule, but this one is easy enough where we can bring that z up. It's not wrong if you did quotient rule. It's just there's an easier way with power rule. Okay, so let me rewrite this. Okay, let's find the derivative. Sine theta becomes. Remember, related rates here, so we also need to include what? D theta dt. Okay, power rule. 15z to negative 1 becomes z to the negative 2 dz dt. Okay. Okay, so hopefully your steps with related rates is coming back here, right? Every variable gets a time treatment. So we're done with the calculus. Now we're just trying to figure out how to put in the values so that we can solve for d theta dt. Any questions so far? All right, so let me do some cleanup here. I want to put that 15, sorry, that z back down in the denominator here. Okay, let's take a step back and look to see what we have. So z equals 25, so that can go into here. D theta dt, that's the unknown variable that's showing up. We know we're looking for that. And dz dt, we have that as well. Okay. Now, what's the one remaining thing that we haven't found yet? We're trying to solve for dz dt. Is there any piece that we still don't have yet? I'm sorry, we're trying to solve for d theta dt. Is there any piece of the puzzle that we still need to find? Yeah. Okay, so on that note, it's theta related, but we're not going to find theta. We're going to find cosine of theta. Okay, we're going to find cosine of theta. I think that's something that a common issue that students have is trying to figure out what theta is, but we don't need to find what theta is. We're going to find the trig ratio at this moment in time. Okay, so to replace that cosine theta, we're going to revisit our triangle. And let's see if we can fill out what is the side length of this triangle at this moment in time. Okay, we know 15 is always staying put. At this moment in time, z is going to be what? 25. And can I figure out what this side length is? Using what? Pythagorean theorem, right? This is variation of 3, 4, 5 right triangle. So a squared plus b squared equals c squared. We can use our calculator, work that out, or we can figure that out that it's going to be 20, right? 20. Okay. So what is the cosine of theta now that we have this triangle built for this moment in time? Adjacent over hypotenuse, so what? 20 over 25, which reduces to be what? Over 5. Okay, so this is the piece that is going to feel new with our related rates problem. But really, this is the only thing that's new, right? Yeah, so the biggest issue students have here is trying to figure out what theta is, but you're not going to know what theta is. You're going to go and find out the entire cosine of theta. You're going to find that entire trig ratio. Okay, so now everything is available for us to solve for d theta dt. So now we're going to put everything in, right? 4/5 in for cosine theta, 25 in for z, and z dt is -1, and the rest is our calculator. Okay, so let's see if we can get this all cleaned up and use our calculator to get to our answer here. So cosine theta, 4/5. Okay, we can divide by 4/5, which is the same thing as multiplying by the reciprocal. The two negatives can cancel out here. So 0.03 or 3 over 100, either is acceptable. Now, anytime we're dealing with theta and we're trying to find the units of measure, theta is always going to be in terms of radians, and t is going to be whatever time unit we're given here, so per second. So it's always going to be radians per time unit. Any questions here? Okay, so let me recap. With trig related rates, we're always going to be, we know whatever the scenario is, we can always fit our problem into a right triangle. There's always going to be a theta that's going to be involved, and we're always looking for d theta dt, or d theta dt is always going to be involved in that process. And we're going to have to look at what's given to us and decide, can we use sine, cosine, or tangent? Sometimes we have more flexibility in terms of choosing which trig equation we want to use. Sometimes we have more information that we need, but in this case, we're forced into sine. Okay. And then once you create your trig equation, you find your derivative, get your d over dt's to show up, and you're going to always be looking for a trig ratio that's missing. Okay, you're not going to know what theta is. You're going to find the trig ratio. So you're going to draw a second triangle here, figure out the ratio at that moment in time, and then you can put that value in. Okay, let's skip number 2 and let's go to number 3 here. Okay, we're going to revisit a old problem that we've seen, the ladder problem. So we'll skip part B, just in terms. Maybe we'll come back to part B, but really just want to do A as a way of reviewing our familiar ladder problem, and then we're going to use information from part A to get to part C. All right, so a ladder 50 feet long is being pushed against a wall at a rate of 5 feet per second. When the bottom ladder is 30 feet from the wall. So I'm going to call this X, Y, and Z. Okay, so we know Pythagorean theorem is going to relate these three sides here. And I want to make sure I save enough space so I can get to part C here. Okay, so derivative 2x dx dt. All right, we have 6 variables in play here, so we can list them out. Okay, ladder 50 feet long, where does that go? Pushed against the wall at a rate of 5 feet per second. That's referring to what? Dx over dt. Now, what's happening to x as the ladder is getting pushed towards the wall? Okay, it's changing. Do we need to make any adjustment with this? Getting shorter, right? X is getting shorter, so we want to make the adjustment by calling this -5. Yeah, dx dt, -5. Okay, when the bottom ladder is 30 feet from the wall, X. What is the velocity of the top of the ladder? What are we looking for? dy dt, okay. The rest we can kind of figure out on our own here. This is a moment in time here, so what can we know? What we know about y here? Yeah, 3, 4, 5 right triangle. We can also do Pythagorean theorem and understand that we plug that in and solve for y. So this ends up being 40. Right? What about dz dt? The rate of change of the hypotenuse, 0, right? That ladder is going to stay 50 feet from the beginning to the end of the problem is never going to change. The rate of change of that ladder is 0. Stays 50 the entire way through. Okay, everything we need is here for us to solve for dy dt. So we can put all this into our equation here. Okay, this is convenient here. This wipes out to be 0. Ends up being -300. We can add that 300 over to the right side. Okay, divide by 80. Right. This positive value should make sense because as the ladder is getting pushed, the bottom ladder is getting pushed against the wall. This top ladder is rising, so that's going to cause the y to increase. So that positive value does make sense, right? What's our unit of measure here? dy dt, feet per second. Okay, so that's all review, right? We know how to do this. In interest of space here, let's go to part C. This area problem is going to be 1/2 xy. We'll go through product rule. Okay, we've seen that before, but we can always revisit that later. Let's look at part C. At what rate is the angle formed by the ladder and the floor changing at that time? So we're looking for what? Yeah. At what rate is the angle changing? What are we looking for though? D theta dt. Yep. Okay. So in this case, we can actually use any trig equation because we have more than enough information, and we can either use sine or cosine or tangent. My suggestion is that we would like to take advantage of a constant so that we can avoid quotient rule. So anything that can involve the 50 is going to be the easiest way. So either cosine or sine can take advantage of that constant that we have up here. Okay, so constant allows us to avoid quotient rule. I mean, we can use tangent as well, but if we do tangent, we got to make sure we include quotient rule. So we can use sine or cosine. Because we use sine from the previous problem, let's use cosine just for practice purposes so we can have more chance to see all the different variables at play here. So I'm gonna, but if we use sine or if we use tangent, we should all still get the same answer. Okay, so we're gonna set things up here where we can start our equation with cosine. So what would this look like? Cosine theta equals what? Okay, we can find our derivative. Cosine theta becomes, don't forget what? D theta dt. And what rule can we use on the right side? Power rule, right? There's no need for quotient rule. What's another way to view x over 50? Yeah, 1/50th times x, right? It means the same thing, but if it makes it easier for you to see the power rule step, if you want to write it that way, that's fine. Okay, what's the derivative of 1/50th x? Times. Yeah, remember with related rates, we have to do something with the x as well. The x also is getting impacted by time. Okay, so do we have dx dt? Yes, right. So what's the last piece that we need before we can solve for d theta dt? Yeah, we want to find not just theta, we want to find sine of theta. Okay, sine of theta. So let's draw another triangle so that we can kind of just focus on the parts that is going to matter to us most. Let's fill out all of this triangle with numeric values for this moment in time. So x is 30, y is 40, z is 50. What's sine of theta? Which can reduce to be 4/5. Now, this is the new piece that we haven't learned yet, right? This is the thing that's going to feel new about these related rates problem. Creating that second triangle, getting that ratio replaced, replacing our trig function, and then, okay. So we should be in the clear now. We should be able to solve for d theta dt. Everything that we need is in front of us. clean this up, divide by -4/5, which is the same thing as multiplying by 5/4 or -5/4. .125 or 1/8. What's our unit of measure? Theta, so always radians, never degrees, so radians per time unit, radians per second. Okay, let's look at example 4. A television camera at ground level is filming a liftoff of a space shuttle that is rising vertically according to our position function, 50t squared. So this is going to tell us any moment in time is going to tell us how high that space shuttle is off the ground. S is in feet, T is in seconds. Find the rate of change in the angle of elevation of the camera shown below at 10 seconds after liftoff. So again, we're looking for what? Yeah, d theta dt. That's our goal. 10 seconds after liftoff. Okay, so let's see if we can gather enough information. So we have to involve theta, we have to involve 2000, and we have to involve S. So which trig equation can we use that will hit all three pieces there? Yeah. Tangent, okay. So what would that look like? Tangent of theta equals S over 2000. Okay, we start off with this trig equation. Now we can move on to our derivative. Tangent theta becomes, what's tangent's derivative? Secant squared times d theta dt. And what rule can we use on the right side here? Just power rule, right? S over 2000, the same thing as 1 over 2000 times S. It's just, we can just think of it as some number in front of my variable. So what's the derivative of 1 over 2000 times S?
Over 2.
1 over 2000. Anything else?
Yeah, so
ds dt, good. Okay. What does ds dt represent? Yeah, another word for rate of a rocket is the what of the rocket. Has to do with this here. If S of t is 50t squared, ds dt is what? What's another word for derivative? Okay. How about if I say this? This is position. The derivative is what? What we call the derivative of position. Velocity. Yeah. So basically, I want to just help you understand that ds dt is really talking about the velocity of this rocket at the moment in time. Okay. So ds dt or s prime. Let's build a derivative here. So s prime is equal to what? 100t. We want to find out 10 seconds after liftoff. So the moment in time that we're talking about is 10 seconds in. So how can I find the velocity at 10 seconds? Plug in 10, yeah. Okay, so DSDT is 1,000. We know that's going to go in for that piece here. We have to figure out what secant of theta is so that we can make that substitution. But again, we have to go to our, let's build a second triangle so we can find that ratio, right? So let's fill out the triangle here. We know this is 2,000. How can I find the height of this triangle? Good. Plug 10 into the original function, right? This S of t, I want to find out how high the rocket is 10 seconds in. So S of 10. Which is 5,000 feet. All right. Now, to find secant, we need to have the hypotenuse as well. So what can we do to find the hypotenuse? Pythagorean theorem, right? It's a large number, but you have your calculator. So a squared plus b squared equals c squared. We're getting a pretty messy number here, ends up giving us 29 million. And we got to get the square root of that, right? Okay, we'll hold on to this messy number because eventually things will clean up a little bit more. But what's secant of theta now that we have all three sides for this moment in time evaluated? Good. Hypotenuse over adjacent. We know secant is the reciprocal of cosine, so hypotenuse over adjacent. Okay, so that's the last piece of the puzzle that we need. Now everything is just putting in and trying to solve for d theta dt. Yes, question.
Is it secant squared?
It will be, yeah. So I'm going to put that in, and then I'm going to square it after I put that ratio in. Yeah, but I am going to square it, yes. It's a lot of messy numbers here, but it will clean up for us. Any questions so far? Okay, so I've replaced secant theta with this messy ratio. Make sure I'm squaring that. DSDT is 1,000. That cleans up to be just 1 over 2. I can square that expression here, make it 29 million over 2,000 squared. I know the 1,000 over 2,000 is just 1/2. So dividing by this fraction is the same thing as multiplying by the reciprocal. Right, let's see what we can do to clean this up here. This messy fraction gets me all the way down to 4 over 29. I can continue to reduce. The 4 over 2 becomes just 2 up top. So I get 2 over 29. That's my answer. What's my unit of measure? Radians per second. Okay, let's do one more here. Let's go to page 17 and let's look at 38. Okay, balloon rises at a rate of 4 meters per second from a point on the ground, 50 meters from an observer. Find the rate of change of the angle of elevation of the balloon from the observer when the balloon is 50 meters from the ground. So we know that this is not changing here. The balloon is going to be rising. Theta is changing. Y is changing. Okay. All right. Which trig equation can we use to start off? Tangent. Okay. Tangent theta equals 50. Okay. Derivative. Power rule, y over 50 is the same thing as 1/50th times y. Okay, balloon rises at a rate of 4 meters per second. What can we assign that to? Okay, d by dt, positive or negative? Yeah, because as the balloon is rising, that y, that distance to the ground is going to be increasing. So from a point 50 meters, let's see, when the balloon is 50 meters above the ground. So this is a moment in time when y is equal to 50. Okay. So we have dy dt. Now we got to figure out what secant of theta is, right? Not just theta. We want to figure out secant theta. So we'll draw a second triangle. So we just focus on what we want to gather. Okay. What can we fill in for this triangle for this moment in time? 50 and 50. Pythagorean theorem, a squared plus b squared equals c squared. If you also recognize this as a 45, 45, 90 triangle, which a little bit of a shortcut, we can say this must be 50 root 2. But you can also figure that out using Pythagorean theorem. Okay, so the thing that we're looking for to move forward is that secant theta for this moment in time ratio. What's secant of theta? And what's nice about this, we can reduce it down all the way down to what? This root 2. So we're almost there. Just have to put this piece in for that. And then we can work towards solving for d theta dt. Root 2 squared is just 2. Divide by 2 or multiply by 1/2. Yes, question.
How'd you get secant of theta to equal square root of 2?
Oh, so it's 50 root 2 divided by 50 is hypotenuse over adjacent. And I just reduced it.
Yeah, I got like square root of 5,000.
Oh, yeah, square root of 5,000. It should be the same, right? You got 50 squared. So yeah, so 5,000 is same thing as square root of 2,500 times 2. And 2,500 is a perfect square, so we can pull that out as 50.
So can I
Root two.
leave it?
Yes, yeah, you can leave it as square root of 5,000. And if you once you square it, it'll come out cleanly to be just 2. Yeah. Okay, reduce that even more. I get 2 over 50, which is same thing as 1 over 20. Let's see here. Sorry, 4 over 100, which is same thing as 1 over 25. Is that what you guys got? 1 over 25? Okay. Okay, so we'll definitely run through more related rates next week. But Monday, we're going to do inverse trig derivatives. That's the last set of derivative rules. So one last new topic Monday, and then we'll switch it to derivative mode. Okay, come get your phones.
Yeah, like I did it, your 5 just a little. Yeah.